then I would like to welcome my next speaker, Maximilian. What will you be talking about, Maximilian?
I'm talking about, can you hear me?
Yeah.
Ah, perfect. I'm talking about some solutions to enhance the multi-camera setups for GigE Vision. And I will, in detail discuss two functionalities that we bring with our iVium GigE cameras. And with this, actually, should I already start? Yes.
Yeah, sure. Go ahead.
So I really welcome everyone to the presentation about the next level of multi-camera performance for GigE Vision. My name is Maximilian Pockensee. I am the product manager for the iVium G1, the iVium G5, and our accessory portfolio at Allied Vision. So where's the pointer?
There it is.
This one?
Yep.
In the middle?
Forward.
Forward, backward?
Forward, backward, and this one is for the pointer.
Okay, thanks. So let's get started. Just some brief overview about our agenda today. First, I give an introduction about Allied Vision Technologies as a company. Then we'll move over to give you a little background about the GigE Vision protocol and the reliability of it. Then we talk about the challenges of GigE Vision multi-camera systems, and then we basically get to the core of the presentation, which is on the one hand Ethernet flow control and TCP and offloading. And at finale, I will tell you a little bit about our iVium GigE cameras. So just a bit about Allied Vision. We are a machine embedded vision camera supplier since 1989. We have more than 250 employees. The headquarters is in Germany, but we also have manufacturing facilities. Our manufacturing facilities are in Germany and Canada. What we also have are direct sales representations in Europe, USA, Singapore, and China. We have expertise in the field of hardware, embedded software, and host software. And we're active in the fields of visible, infrared, and UV area scan imaging. What we also do is custom OEM development, and we are part of the TKH group. And TKH group also has expertise in line scan and 3D imaging, also amongst others. It's kind of a broad field where we are active. Yeah, and that's so far about Allied Vision technology. So let's get started with the actual topic. So first about the GigE Vision protocol. GigE Vision sits on top of very common network technology. And these are the core protocols: GigE Vision Control Protocol, GVCP, and GigE Vision Streaming Protocol, GVSP. And they are based on the User Datagram Protocol, UDP. And UDP is really most widely used in machine vision. And that's for a reason. It allows efficient and low latency transmission of data. It only needs a very small header necessary for the data transmission. And it focuses on speed and simplicity. Moreover, it does not require any prior handshake between the camera and the host system. So there's no handshake necessary. But there are also some downsides to UDP. And I really want to talk about the limitations. There's an inability to detect and correct data, which get lost on the way. There is no guarantee of the right order of datagrams or packets. And they are really sensitive, or UDP-based systems are really sensitive to network congestion or system overload. So you can basically describe the way of data transmission as fire and forget. So you send the data out and UDP doesn't really care what's happening with it. So you can also say hope and pray that the data is delivered. Moreover, what you can also, or maybe to go back to this, what's really important to note here that are really per se characteristics of UDP-based systems, not GigE Vision as itself. But what GigE Vision does is it adds some reliability functions to UDP. So the order and comprehensiveness of data is ensured through the GigE Vision protocol. And the device sends additional information in each stream packet header. And that allows the host to check whether packets or complete frames are missing. What it also does, if the host determines that packets have been missed, it may send a request to the camera to repeat the transmission of missing packets. This is also called packet reset mechanism, one of the main benefits of GigE Vision as an interface, and especially over USB 3, for example. And it really adds reliability, but can temporarily increase the system overload. And it requires to reserve enough throughput margin during the system design. And if we talk about reliability and packet reset, we also have to talk about frame buffers, or packet buffers. So the typical cause of packet loss in loaded, high throughput systems is the overflow of packet buffers and network devices. And if we talk about packet loss, we basically mean lost frames or lost images. So such hardware buffers are found in network switches and network interface cards. But they also found the cameras, and then they are called image buffers or frame buffers, mostly found in GigE Vision-based cameras, but also sometimes in USB cameras. And they usually buffer only milliseconds of small throughput, which means that even a small temporary congestion event may lead to a loss of several packets. And recent packets from camera increase the load, which may cause even more congestion. So this kind of self-amplifying congestion situation may finally cause to a loss of image data. And maybe just some basic demonstration how this would look like in a regular UDP-based GigE Vision setup. Imagine you have two cameras. You can see them on the left-hand side. They're streaming data through a switch to the host PC. If now both cameras send more data to the switch than usual, for example, if they're triggered or they're going into burst mode, the host at some point gets overloaded and can't process any additional data. So when that happens, the switch will buffer the image data from the camera in its temporary buffers, since it can't send any additional data to the host. And if the image buffer of the switch is full, or better say the switch is overloaded, it will start to drop any additional packets. And the result are really corrupted images or lost images, and that's not really what you want in your application most of the time, of course. So what can you do? So how to improve the system performance of multi-camera GigE Vision systems? Today we talk about two ways to do that, and that's either distribute the system load or reduce the system load. To distribute the system load, I really want to talk with you about Ethernet flow control, which is a feature that's based on UDP. And for reducing system load, we're talking about TCP and offloading, which is a completely different protocol to UDP. And let's take a look first at how Ethernet flow control works. So, same scenario, same situation. The cameras send more data as usual to the host, and as the host starts to get overloaded. The receiver can now send a pause command to the transmitter if it detects a nearly full buffer, which I show here. Then the transmitter stops transmission with the next Ethernet frame for the requested amount of time until it receives a request from the receiver to continue. The data stream to the recipient is now suspended, and the switch will now buffer the incoming data until it observes that it is at risk to get overloaded. And then an interesting thing can happen. It can do the very same thing. It can send a pause command to the camera itself. And it's really important to note here that flow control is really based point to point. So every network or any device between the host and the camera can send such a pause command. And now the camera will buffer the incoming data from the image sensor. And the good thing here is most of the time cameras have a much larger buffer than the network devices have. When the host overcomes the temporary overload, the cameras and switches resume streaming data to the host, and then the camera can also start streaming or forwarding data to the switch. And it really means as long as Ethernet flow control is enabled in your system, it really helps to better utilize the capabilities of the host system of the network devices. And as long as there's enough mean throughput in your system design, you really don't have any loss of packages or any drop frames or any corrupt images. So, as I said, Ethernet flow control, it's really good to better utilize the system. Flow control is enabled by default in all Albion-based GigE Vision cameras. And almost every network device, every network interface card supports this feature. At least every modern switch or network device we know. And users only must make sure the feature is also enabled on the network device side. So that adds really more convenience to design a reliable high throughput system with the limitations of technology, budget, and time. And to sum it up, packet loss to do congestion events is a typical issue in high throughput machine vision systems. And the Ethernet flow control mechanism helps to improve the utilization of these buffers throughout the whole system, so that can absorb temporary congestion events much better. So now we talk about the other mechanism, and that's TCP and offloading. TCP and offloading, as I told you, is a completely different protocol. It's not UDP, it's TCP, and it works in a completely different way in the sense of transmitting data. So before any data is transmitted, a three-way handshake is done between the host and the camera. And now I actually show only one camera, the switch, and the host because it would get too complicated if I show it with a multi-camera setup. So, as I said, before any data is transmitted, a three-way handshake is done to establish an actual connection. So first the host sends a sync request to the camera confirms this with a sync acknowledgement, and then the host reassures with an acknowledgement that data can now be streamed to the host system. So what now happens, every time the camera transmits data to the host confirms that it received the data with an acknowledged package, as you can see here. And it really happens every single time. And in contrast to UDP, TCP only sends the next portion of data when it received an acknowledgement from the host side for the already transmitted data. And the clever thing really is, with these acknowledged packages, the host also signals the camera how much data it will be able to handle until it sends the next acknowledgement. That's called window size. So what it basically means, the camera and the host system are in constant exchange about the level of utilization. And basically, let's look what happens in the case of an unexpected event. For example, in a multi-camera system, several cameras get triggered simultaneously. So packet 3 gets sent to the host. The host is processing this packet, and after it has done it, it realizes, oh, okay, I'm at the edge of getting overloaded. And now the host just waits to send the acknowledgement until it receives, or until it's able to process additional data again. What happens now is that the camera, again, buffers the incoming image data from the sensor in its internal buffers. And it does so until the host system sends the next acknowledgement, which then means it sends out the additional data in the scope of the window size that had been handled out between the host system and the camera. So, and that really means there is not really a risk of having lost images in the system as long as the camera has enough buffer to catch up these temporary events. So let's talk a bit or go more into detail about the benefits of TCP, because it was just a really basic mechanism on how that works. There are standard offload mechanisms available, which means less CPU load. I will go more in detail about that in the next slide. The integrated TCP flow control helps to avoid unnecessary transmission of data that would get lost on the way, so there's less congestion. And it's really important here to understand that GigE Vision actually is a fallback solution of UDP with its packet resend mechanism, while with TCP it's part of the protocol itself, of the TCP streaming protocol. And it really focuses on full frame delivery, so there are no corrupted or partial images. Drop frames, however, are possible. And it's really a reliable connection, so a frame is always delivered completely. Let's also talk a bit on how TCP helps to relieve the host system. I didn't show that in a demonstration I showed you. And that's happening through kind of a feature that's called large receive offload, LRO. And with this feature, the NIC and the network interface card, and that's really important to note that it's happening there, combines multiple received TCP packets into larger ones. So you can basically think about it as this. So there are less and bigger packets that need to be handled by the host, which means less CPU overhead and increased efficiency. And the processing overhead per packet is often big, really quite huge, compared to the effort for processing the actual data of the packets. And this is the reason why reducing the number of packets can effectively reduce the system load. This feature, especially in the world of Windows, is also known as receive segment coalescing, RSC, just for your record. So maybe to give a little bit of a conclusion when to use UDP with flow control and when to use TCP and offloading. If partial images are acceptable, so if corrupted images are not that much of a problem for you, then UDP and flow control can be the better solution, and TCP and offloading TCP and offloading might be the worst solution, and UDP and flow control is the better solution. But I think the main decisive factor here is the interface speed. So UDP comes to a limit for any interface speed of above 5 GigE. So for cameras with 5 GigE or less power, UDP and flow control is used, whereas TCP and offloading is mainly used for cameras of 5 GigE and more, 10 GigE, 25 GigE, and so on. And it's really because the protocol TCP is much more profound and it needs to have a much bigger FPGA on the camera side. Maybe also interesting to note that multicast is not possible with TCP, but it is available with UDP. And the level of data transmission is packet-based with UDP, where it is stream-based with TCP. So just a brief overview about our Alvium GigE cameras that actually support these features. So we have 2 levels of interface performance with Allied Vision's very own ASIC chip. That also means we are a little bit more independent from the current supply chain situation. We have a very attractive sugar cube form factor. So the Alvium G5 is only 60 millimeters long, whereas the Alvium G1 is only 41 millimeters long. We have 25 and even more sensors, including UV visible, near, and SWIR available, which also means global shutter, rolling shutter. It's all in these platforms. We have a comprehensive feature set. We offer superior image quality through fixed pattern noise correction, defect pixel correction, and an active sensor alignment during our automated production process. And we also offer a lot of flexibility because we have C, CS, and S-mount options available. And of course, the cameras are also fully industrial grade. So that means they have long-term availability and reliability and a really wide operating range. So that's actually it. Thank you a lot for your attention. And happy to receive some questions if you have.
Thank you. So thanks, Maximilian. Do you have questions for him? Any questions from the audience? Yes.
The TCP mode you mentioned but this is not the GigE Vision standard, right? It's an Alvium special mode or something?
I think it's still discussed in the standard committee. Felix, correct me if I'm wrong. Yes, my colleague is there. It's still discussed in the standard committee, so we hope that it will be part of the GigE Vision standard at some point, but at the moment it is not.
Yeah, that would be my question as well. How do you participate in the standard development in itself? So I assume that Allied Vision is a part of the GigE Vision standard development team as well?
Yeah, of course. So there are actually discussions already going on about it. We're also not, I think we are not the only company that's investing into this functionality in this protocol. And yeah, as I told, it's especially useful for interfaces that support 5 GigE or more. So also for 10 GigE, it's quite interesting to do so. And I think at the point when interface speed reaches 25 GigE or more, then other mechanisms come into play, other protocols. So. Yeah.
So on your slide, you had there was a comparison between applications where you would use TCP and UDP. Could you give us some examples? So you said that in applications where you can accept a few image drops is okay. Could you give us some typical examples from the real world?
Yeah, I think as I told, the main decisive factor is really the speed of the interface. So if you have, for example, you have 8 5 GigE cameras and that are streaming data to one host system through switch. Usually, just the handling of packets itself is really demanding for the host PC, and the data load is already quite demanding. So it's much better if you have really multiple 5 GigE cameras from us to consider TCP, but it also takes some efforts to implement the system. It's not as straightforward as with UDP. Whereas UDP is much easier if you maybe have less cameras in play and you don't want to actually engage with a completely new protocol that you're not aware of.
Yeah, for example, you talked about multicast. So that's where UDP.
So with multicast, exactly, that's only possible with UDP. It's not possible with TCP at all.
Sure, yes.
Yeah.
But where I was coming from, what my question was coming from, is from a real-world perspective. From what kind of an application would you say, some image drops is okay in this case?
Okay. I mean, you have, if you think about an application like bottle inspection, then image drops are completely unacceptable. If you have, for example, a scanning device for rental cars, it's not a problem if you miss a little piece of the car, maybe. Then
Okay.
that's the thing I mean.
Yes,
So,
this
yeah.
is exactly what I was looking at. Perfect.
Thanks.
Thanks a lot for the talk. I hope you found it interesting as well.